Welcome! In this session, we'll dive into problem number 826, most profit assigning work. We'll explore an efficient way to assign jobs to workers for maximizing profit. Let's get started. In this problem, we are tasked with assigning workers to jobs in a way that maximizes the total profit. Each job has a specific difficulty level and a corresponding profit, represented by two arrays, difficulty and profit. Each worker also has a maximum difficulty level they can handle, given in the worker array. A worker can only take on a job if the job's difficulty is less than or equal to the worker's capability. Importantly, a worker can be assigned at most one job, and they earn the profit associated with that job. If no job matches their capability, they earn nothing. The goal is to determine the maximum profit we can achieve by optimally assigning jobs to workers. The output of the problem is a single integer representing the maximum total profit. To understand this better, let's look at an example. Suppose we have the following input: difficulty is 2, 4, 6, 8, 10, profit is 10, 20, 30, 40, 50, and worker is 4, 5, 6, 7. Here, there are 5 jobs with increasing difficulty levels and corresponding profits. For the workers, their maximum difficulty levels range between 4 and 7. The task is to assign these workers to jobs in a way that maximizes the total profit. Breaking this example down further, the jobs available are: Job 1 with difficulty 2 and profit 10, Job 2 with difficulty 4 and profit 20, Job 3 with difficulty 6 and profit 30, Job 4 with difficulty 8 and profit 40, and Job 5 with difficulty 10 and profit 50. The worker's capabilities are as follows: Worker 1 can handle difficulty 4, Worker 2 can handle difficulty 5, Worker 3 can handle difficulty 6, and Worker 4 can handle difficulty 7. The optimal assignments for maximum profit are: Worker 1 takes Job 2 for a profit of 20, Worker 2 also takes Job 2 for a profit of 20, Worker 3 takes Job 3 for a profit of 30, and Worker 4 takes Job 3 for a profit of 30. Adding these up, the total profit is 20 plus 20 plus 30 plus 30, which equals 100. Now, consider another example where difficulty is 85, 47, 57, profit is 24, 66, 99, and worker is 40, 25, 25. Here, the available jobs are Job 1 with difficulty 85 and profit 24, Job 2 with difficulty 47 and profit 66, and Job 3 with difficulty 57 and profit 99. The worker's capabilities are Worker 1 with a maximum difficulty of 40, and workers 2 and 3 with a maximum difficulty of 25 each. In this case, none of the workers can handle any of the jobs since their maximum difficulty levels are all below the minimum job difficulty of 47. As a result, no jobs are assigned, and the total profit is 0. When solving this problem, there are several edge cases to consider. First, if the worker array is empty, no jobs can be assigned, so the output will be 0. Second, if all workers have capabilities below the easiest job's difficulty, the output will also be 0. Third, since the difficulty and profit arrays may not be sorted, the solution must account for this and handle the data appropriately. Lastly, for large inputs where both n and m reach their upper bounds, the algorithm needs to be efficient enough to process arrays of size up to 10,000 without running into performance issues. These considerations ensure that the solution is robust and works for all valid inputs. To start, let's consider the brute force approach, which is the most straightforward way to solve this problem. The intuition here is simple: for each worker, we determine the best job they can handle by comparing their ability to the difficulty of every available job. The goal is to find the job with the highest profit that the worker qualifies for. Specifically, we iterate through each worker in the worker array, and for each one, we check all jobs in the difficulty array to see if the worker's ability is sufficient to complete the job. If it is, we keep track of the job's profit and update the maximum profit the worker can earn. Once we've calculated the maximum profit for all workers, we sum these up to get the total profit. However, this approach has a downside: its time complexity is O, n*m, where n is the number of workers and m is the number of jobs. This is because we're essentially performing a nested loop over the workers and jobs. While this method is simple and requires no additional space, it becomes computationally expensive as the input size grows, which limits its practicality for larger datasets. While the brute force approach is easy to understand, it has some significant trade-offs. On the positive side, it's straightforward to implement, making it a good choice for smaller inputs or when prototyping a solution. However, the inefficiency of iterating through every worker job pair makes it unsuitable for larger input sizes. To address this, we can use an optimized approach that leverages sorting and binary search to reduce redundant comparisons. Here's the key idea: instead of comparing each worker with every job, we pre-process the jobs into a sorted list based on their difficulty and profit. This allows us to efficiently look up the best job for any worker. One important observation is that for any given difficulty level, we only care about the job that offers the maximum profit. By sorting the jobs, we can ensure that as difficulty increases, the corresponding profit is also maximized. Additionally, sorting the workers by their ability allows us to process them in ascending order, ensuring that we only consider jobs that are feasible for each worker. Using binary search, we can quickly determine the most profitable job a worker can handle, significantly reducing the time complexity. Let's break down the steps of the optimized approach. First, we pair the difficulty and profit arrays, creating a list of jobs that we then sort by difficulty. While doing so, we make sure that the profit values are adjusted such that for any difficulty level, we track the maximum profit achievable. This ensures that as we move through the list, the profit is non-decreasing. Next, we sort the worker array so that we can process them in ascending order of ability. For each worker, we then use binary search or a two-pointer technique to find the highest profit they can achieve based on their ability. By summing up the profits for all workers, we arrive at the total profit. This approach is much more efficient, with a time complexity of O, m log m plus n log m. Sorting the jobs and workers each takes O, m log m, and O, n log n, respectively, while the binary search for each worker runs an O, log m. The space complexity is O, m, as we need to store the sorted list of jobs. While this method is more complex to implement compared to brute force, it offers substantial performance benefits, particularly for large input sizes, making it well worth the additional effort. The optimized approach, with its use of sorting and binary search, is the strategy we've chosen for this problem. It strikes the right balance between efficiency and clarity. While the brute force method is simpler to implement, its inefficiency makes it impractical for handling large inputs. The optimized approach avoids redundant comparisons by pre-processing the jobs into a structured format and efficiently querying them for each worker. The critical realization here was that sorting both the jobs and workers allows us to process them systematically, ensuring that we never revisit infeasible jobs. Additionally, pre-computing the maximum profit for each difficulty level eliminates the need to evaluate lower profit jobs repeatedly, further improving efficiency. This approach provides a scalable solution with a time complexity of O, m log m plus n log m, making it well suited for competitive programming and real-world scenarios where performance matters. By combining thoughtful pre-processing with efficient querying, this strategy not only meets the problem's constraints but also highlights the importance of leveraging sorting and binary search to optimize complex tasks. The goal of this problem is to assign workers to jobs in a way that maximizes the total profit. Each worker has a maximum difficulty they can handle, and each job is defined by a difficulty level and a profit value. For every worker, we want to find the job with the highest profit they qualify for, based on their skill level. To solve this, the brute force approach begins with input parsing. We are given two arrays, difficulty and profit for the jobs, and an array worker indicating the skill level of each worker. Our task is to determine the best job for each worker and sum up the profits. First, we iterate through each worker, initializing a variable max_profit to 0 for each. This variable will store the highest profit the worker can achieve based on the jobs they qualify for. For each worker, we compare their maximum ability with the difficulty of all jobs. Specifically, we check each job defined by its difficulty D_I and profit P_I. If the worker's ability is greater than or equal to the job's difficulty, it means they qualify for that job. In this case, we compare the job's profit with the worker's current max_profit. If the job's profit is higher, we update max_profit to this new value. After evaluating all jobs for a worker, we add their max_profit to a global variable total_profit, which tracks the overall profit across all workers. Once all workers are processed, the final total_profit is returned as the result. This approach ensures correctness but is computationally expensive. With n workers and m jobs, the nested iterations result in a time complexity of O(n*m). The brute force approach guarantees that each worker gets the most profitable job they can handle, making the solution correct. However, the downside is the high computational cost due to the nested loops. To improve efficiency, we can optimize the process by reducing redundant comparisons. One key optimization is to sort the jobs by their difficulty. By doing this, we can pre-compute the maximum profit for each difficulty level, ensuring that the profits are non-decreasing as the difficulty increases. Another optimization involves using binary search to quickly find the most challenging job a worker can handle. Combining these strategies, we can significantly reduce the time complexity to O(n*log_m, where log m comes from the binary search. To implement the optimized approach, we leverage specific data structures. First, we store the jobs as a list of tuples, where each tuple contains the difficulty and profit of a job. Sorting this list by difficulty allows efficient binary searches and eliminates redundant evaluations. For the workers, we can directly iterate through their skill levels. However, if the worker list is sorted as well, it simplifies the comparison process when paired with the sorted jobs. The optimized approach starts by sorting the jobs based on difficulty. Then, we pre-compute the maximum profit for each difficulty, ensuring that profits are non-decreasing. For each worker, we use binary search to identify the most difficult job they can handle. This allows us to directly fetch the pre-computed maximum profit, making the process efficient. With sorting taking O(m*log_m and binary searches for each worker taking O(n*log_m, the overall complexity is O(m*log_m plus n*log_m. When implementing this algorithm, it's important to consider edge cases to ensure robustness. If either the jobs list or the worker list is empty, the total profit is simply zero because no assignments can be made. Another scenario involves jobs with the same difficulty but different profit values. Here, we must ensure the maximum profit is selected by pre-computing the non-decreasing profit for each difficulty. Finally, there may be workers whose ability is too low to handle even the easiest job. These workers contribute zero to the total profit since no jobs are within their capability. To illustrate the algorithm, consider an example where difficulty equals 2, 4, 6, 8, profit equals 10, 20, 30, 40, and worker equals 5, 10, 3. We will evaluate the assignments and calculate the total profit for these inputs. Let's walk through the execution with both the brute force and optimized approaches. Using brute force, for worker 5, we compare their ability with all jobs. The highest profit they can earn is 20 from the job with difficulty 4. For worker 10, the best profit is 40 from the job with difficulty 8. For worker 3, the best profit is 10 from the job with difficulty 2. Summing these gives a total profit of 70. With the optimized approach, we start by pre-computing the maximum profit for each difficulty, resulting in 10, 20, 30, 40. Using binary search, we quickly find the most difficult job each worker can handle and fetch the corresponding profit. Worker 5 earns 20, worker 10 earns 40, and worker 3 earns 10, resulting in the same total profit of 70. The optimized approach achieves this with significantly reduced computational effort, demonstrating its efficiency and correctness. This Python implementation solves the LeetCode problem most profit assigning work by efficiently matching workers to jobs they are qualified for. The goal is to maximize the total profit while adhering to the constraints of worker abilities and job difficulties. The function maxProfitAssignment begins by combining the difficulty and profit of jobs into a list of tuples. This list is sorted by difficulty to ensure that we process jobs in ascending order of difficulty. Ties in difficulty are resolved by sorting by descending profit, ensuring we always consider the most profitable job first for the same difficulty. Next, we sort the worker array, as this allows us to iterate over workers from least to most capable. This way, we can align workers and jobs in a synchronized manner, avoiding redundant computations. We initialize max_profit to track the best profit available for the current worker's ability, and total_profit to accumulate the overall profit. The job_index pointer is used to traverse the jobs list. For each worker, we assign the best job they qualify for by iterating through the jobs list while the job difficulty is less than or equal to the worker's ability. During this process, we update max_profit to the highest profit seen so far. Once no more jobs can be assigned to the worker, the current max_profit is added to the total_profit. This approach is efficient because sorting the jobs and workers takes n log n plus m log m, and the single traversal of the jobs list ensures the overall time complexity remains linear relative to the combined input size, n plus m. The solution handles edge cases, such as workers with very low or very high ability, by simply skipping jobs they cannot handle or stopping once all jobs are processed. The implementation ensures correctness while maintaining clarity and efficiency. In this implementation, we start by importing the necessary utilities and defining our solution class. The main method, maxProfitAssignment, takes 3 arrays as input: difficulty, profit, and worker. The goal is to find the maximum total profit we can achieve by assigning workers to jobs based on their abilities. First, we combine the difficulty and profit arrays into a 2-dimensional array called jobs. Each job is represented as a pair, with the difficulty as the first element and the profit as the second. This makes it easier to process the jobs collectively. Then, we sort the jobs array. The sorting criteria ensure that jobs are ordered primarily by difficulty in ascending order. If 2 jobs have the same difficulty, they are sorted in descending order of profit. This guarantees that for any given difficulty, we always consider the most profitable job first. Next, we sort the worker array to facilitate a systematic allocation of workers to jobs based on their abilities. We initialize variables maxProfit to track the best profit for the current difficulty level, total profit to accumulate the total profit across all workers, and job index to iterate through the jobs. The for loop then begins iterating through the worker array, representing each worker's ability. For each worker's ability, we use a while loop to evaluate all jobs that the worker can handle. These are the jobs with a difficulty less than or equal to the worker's ability. As we iterate through these jobs, we update maxProfit to ensure it always holds the highest profit among the jobs that the worker is qualified for. Once we've processed all relevant jobs, we increment job index to move to the next job. After determining the best profit that this worker can achieve, we add maxProfit to total profit, which accumulates the total earnings for all workers. Finally, after processing all workers, we return total profit, which represents the maximum profit we can achieve by optimally assigning workers to the available jobs. This approach ensures that we efficiently match workers to the most profitable jobs within their skill range while maintaining an overall time complexity that is manageable for large inputs. Here, we start with a basic example to understand the problem. We are given arrays for job difficulties, profits, and worker abilities. The first step is to combine the difficulties and profits into a list of jobs as pairs of difficulty, profit. After combining, we sort these jobs by their difficulty in ascending order. If 2 jobs have the same difficulty, we sort by profit in descending order, though in this case, there are no ties. The resulting sorted list of jobs is 2, 10, 4, 20, 6, 30, 8, 40, 10, 50. Next, we sort the worker array, which defines the maximum ability of each worker. The sorted workers are 4, 5, 6, 7. Finally, we initialize max_profit to 0, which will track the best profit we can achieve for a given difficulty, total_profit to 0 for the cumulative profit, and job_index to 0 to keep track of which job we are currently considering. Now, we iterate through each worker to calculate their contribution to the total profit. Starting with the worker who has ability 4, we check jobs up to their ability. The best job they can take is, for 20, so we update max_profit to 20 and add it to total_profit, resulting in a total of 20. For the worker with ability 5, no additional jobs are within their ability beyond what we already considered, so max_profit remains 20, and we add it to total_profit, making it 40. Next, the worker with ability 6 can take on a new job, 6, 30. We update max_profit to 30 and add it to the total, which now becomes 70. Finally, the worker with ability 7 cannot take on any jobs beyond the best profit available so far, which is 30. Adding this to the total gives us a final total_profit of 100. Let's examine an edge case where all workers have abilities too low to perform any jobs. The input consists of job difficulties 5, 10, 15, profits 50, 60, 70, and worker abilities 1, 2, 3. First, we combine and sort the jobs based on difficulty, resulting in 5, 50, 10, 60, 15, 70. Since the input jobs are already sorted, no changes are needed. Next, we sort the workers, which yields the array 1, 2, 3. As before, we initialize max_profit to 0, total_profit to 0, and job_index to 0. This setup prepares us to iterate through the workers to calculate their contributions. We now evaluate each worker in the sorted list. For the worker with ability 1, no jobs are within their ability, so max_profit remains 0, and adding it to total_profit results in a total of 0. Similarly, the worker with ability 2 also cannot do any jobs, so the total profit remains unchanged at 0. The same happens for the worker with ability 3, as no jobs are accessible to them either. Since none of the workers can perform any jobs, the final output for this case is 0. In this example, we explore overlapping worker abilities, where some workers share the capacity to perform the same jobs. The input includes job difficulties 1, 3, 5, 7, profits 10, 20, 30, 40, and worker abilities 2, 4, 6. After combining the jobs into pairs and sorting, we get 1, 10, 3, 20, 5, 30, 7, 40. Since the jobs are already sorted by difficulty, no additional sorting is required. The worker array is sorted as well, resulting in 2, 4, 6. As usual, we set max_profit to 0, total_profit to 0, and job_index to 0 to begin iterating through the workers. We start with the worker who has ability 2. The only job they can take is 1, 10, so we update max_profit to 10 and add it to total_profit, which becomes 10. For the worker with ability 4, they can take the job 3, 20, so we update max_profit to 20 and add it to the total, bringing it to 30. Finally, the worker with ability 6 can take on job 5, 30, so we update max_profit to 30 and add it to total_profit, resulting in a final total of 60. This example highlights how workers with overlapping abilities can maximize the total profit by accessing progressively better jobs as their abilities increase. To analyze the time complexity of our solution, let's break it into distinct steps. First, we combine the difficulty and profit arrays into a list of tuples called jobs. This step involves pairing the corresponding elements of the two arrays, which requires a single pass through both arrays. Since their lengths are both n, this operation has a time complexity of O(n). Next, we sort the jobs list based on difficulty, and in the case of ties, by profit. Sorting a list of size n takes O(n log n) time. Similarly, we sort the worker array, which contains m elements, and sorting this array takes O(m log m). These are the preparatory steps before we begin assigning jobs to workers. Now, let's look at the process of assigning jobs to workers. For each worker, we iterate through the worker array, which involves m iterations. Within this loop, we also traverse the jobs list to find the maximum profit achievable by that worker. Importantly, the inner loop doesn't reset for each worker, instead, it continues from where it left off, ensuring that the total number of iterations across all workers is at most n, the size of the jobs list. Operations inside these loops, such as comparisons and updates, are constant time, O(1). Combining these, the complexity of this step is O(n plus m). When we sum up all the steps, the overall time complexity becomes O(n log n plus m log m plus n plus m). Since the sorting steps, O(n log n plus m log m), dominate the other terms, we conclude that the solution's time complexity is O(n log n plus m log m). In terms of space complexity, the jobs list, which stores tuples for all n jobs, requires O(n) space. Sorting the jobs and worker arrays is often done in place, meaning no additional memory is required, but if the sorting algorithm used does require extra space, it would add O(n log n plus m log m). Additionally, the algorithm uses a constant amount of space for variables like max_profit, total_profit, and job_index, which is O(1). Since the jobs list is the largest structure in memory, the overall space complexity is determined by it, meaning the total space complexity is O(n), assuming in-place sorting. Comparing this solution to a brute force approach, we can see significant improvements in efficiency. A naive method would require iterating over all n jobs for each worker, which results in a time complexity of O(m*n). In contrast, our optimized solution sorts the jobs and worker arrays first, and then processes jobs in a single pass for all workers, reducing the time complexity to O(n log n plus m log m). When considering the best, average, and worst-case scenarios, the time complexity remains consistent because the dominant operations, sorting and single-pass processing, occur regardless of input conditions. Mathematically, sorting's O(n log n plus m log m) term is asymptotically larger than the O(n plus m) from the single-pass processing, so it defines our time complexity. For space, the jobs list dominates memory usage with O(n), and in-place sorting ensures no additional memory overhead. This makes the provided solution both time and space efficient compared to the brute force alternative. One of the most common mistakes in this problem involves incorrect sorting logic. Since the algorithm often relies on sorting jobs by their difficulty or sorting workers by their ability, getting this order wrong can cause the solution to fail. For instance, if jobs aren't sorted by difficulty, a worker might be assigned a job they cannot handle, resulting in invalid outputs. Sorting is especially critical in greedy or binary search approaches, where the entire solution depends on processing elements in the right order. Another issue is misinterpreting constraints. For example, overlooking the maximum number of jobs or workers can lead to unnecessarily complex solutions. Misunderstanding these constraints can make your algorithm inefficient, possibly exceeding the time limit due to higher than needed complexity. Lastly, overusing brute force is a common pitfall. If you iterate through all jobs for every worker, the time complexity becomes O(n*m), which is impractical for larger inputs where both n and m can reach 10 to the power of 4. This approach is inefficient and often fails for larger test cases. Another critical error is not handling edge cases properly. Scenarios like no jobs being available for a worker or all workers being unqualified for available jobs are easy to overlook. Missing these cases can lead to runtime errors, such as accessing invalid indices, or result in incorrect outputs. Overcomplicating binary search is another frequent issue. Mistakes here might include failing to correctly update pointers, which could lead to infinite loops, or not handling tie-breaking conditions properly, causing the algorithm to return incorrect indices. These errors are problematic because binary search is often a core part of optimizing the solution, and even small mistakes can derail its effectiveness entirely. To succeed in interviews, it's essential to optimize both sorting and searching. Sorting jobs by their difficulty and workers by their ability is often the first step to an efficient solution. From there, focusing on greedy methods or binary search allows you to minimize unnecessary computations and streamline your approach. It's also important to understand the trade-offs between different strategies. For instance, brute force might be acceptable for small constraints, but for larger inputs, optimizations like prefix sums or binary search are crucial. Mastering edge cases is another key skill, as interviewers often test scenarios like having only one worker, no available jobs, or all jobs sharing the same difficulty. Finally, be prepared to explain your solution's complexity clearly. Whether it's O(n log n or O(n plus m), understanding and articulating how sorting and binary search impact the runtime will demonstrate your expertise. There are several related problems that share similar strategies and concepts. For example, LeetCode 410, split array largest sum, involves dividing workloads optimally, which is directly applicable here. LeetCode 875, Cocoa eating bananas, is another binary search problem where the focus is on optimizing a solution by searching within a range of values. Similarly, LeetCode 1011, capacity to ship packages within D days, also uses binary search with constraints on workload distribution. Lastly, LeetCode 1353, maximum number of events that can be attended, is a classic greedy problem that relies on sorting and selection, offering another perspective on how to approach optimization challenges. There are alternative approaches to solving this problem, each with its own trade-offs. One option is using a greedy approach with prefix sums. By pre-computing the maximum profit for each job difficulty, you can reduce the time complexity of finding the best job for a worker to O(1) after pre-processing. However, this comes at the cost of increased space complexity. Another approach is binary search, which allows you to quickly find the most suitable job for each worker based on their ability. This method requires sorting the jobs and implementing efficient binary search logic, achieving a time complexity of O(n log n) or O(n plus m log n), depending on the implementation. A simpler alternative is the two-pointer technique, which involves iterating through workers and jobs simultaneously, assigning jobs as long as the worker can handle them. While this method is easier to implement, it works best when the input is presorted, and it's less flexible for scenarios where additional optimization is needed. Great job! Today, we reviewed the most profit assigning work problem and discussed a brute force approach. Remember, understanding the basics is crucial before diving into optimizations. Thanks for joining, and don't forget to like and subscribe for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!